will continue the topic of metallurgy. Yesterday we have discussed about the different methods in metallurgy. We reached up to reduction. First one is concentration, second is oxidation, and third one reduction. And we have discussed the reduction of iron ore, then copper ore and aluminum ore. Then after all this method, the obtained metal will not be completely pure. To get ultra pure metal or to obtain 100% pure metal, we have to again refine or purify the obtained metal from reduction. So today we are going to discuss the different methods we can use to purify metals according to their nature. The first simple method is distillation. As we all know that distillation is based on the difference between the boiling points of components. Here metal and impurities, so they should have high difference between their boiling points. This method is usually used for low melting metals like zinc and mercury. You know that mercury is already in its liquid form, so it has very low boiling point, and zinc also has low boiling point. So distillation is used for metals with a low boiling point like zinc and mercury, and at the same time the impurities must have higher boiling point. So on heating the impure metals of zinc or mercury, the only metal will form vapors. On heating, this is we can take the example in pure mercury. On heating, only pure mercury will form vapors, and we can collect it in another vessel, and here we will get pure mercury. So there should be difference between the boiling points of mercury and the impurities. Impurities must have higher boiling point than mercury, then only we can use this method. So distillation is based on the difference between boiling points of metals and impurities. Then second method is liquefaction. Liquefaction is used for low melting metals. This is for low boiling metals. So low melting metals, example we can say that tin. Tin can be purified by this method. So here the metals will have low melting point and the impurities must have higher melting point. So the impure metal is placed on the sloping hearth of a furnace. This is a furnace. It is maintained at a very high temperature and it has a slope. And the impure metal is placed here. We are placing impure tin. Then the only tin will melt and it will flows down, and we can collect the pure metal here. The impurities which have high melting point will remain here. So we have to check the melting point of the metal and impurities, and we have to just keep the temperature just equal to the melting point of tin. Then only, otherwise if we are using very high temperature, both the impurities and tin will melted over and both flows down, and here we will get the same impure tin. So we have to keep the temperature according to like that. So distillation is based on the difference in boiling points. If metal has low boiling point, we can use this method. Usually we are using this method for low boiling metals like zinc and mercury. And liquefaction is used for low melting metals like tin, and the impurities must have higher melting point than metal. The impure metal is placed on the sloping hearth of a furnace. Then at this temperature only metal will flows down, metal will melt and flows down, and we will get the pure metal on the other side of the furnace. That is the second method. Then the third one, that's a very important method, That is called electrolytic refining. We usually discuss this method in lower classes. Electrolytic refining. This method we can use for most of the metals if they are good conductors. Here we are considering the purification of copper. So for this method, the impure block, this is the impure copper. A large block of impure metal is taken as anode and a thin strip of pure copper is taken as cathode. This is acting as cathode and this is acting as anode. So you have to connect the electricity and it is placed in a vessel that is contain an electrolyte. Usually the same electrolyte of the same metal we are using copper sulfate solution. So a big block of impure copper is acting as anode and a thin strip of pure copper is acting as cathode, and they are dipped in a solution of copper sulfate and they are connected to power source. On applying electricity, what will happen? We know that at anode oxidation will take place. So the metal from pure copper undergo oxidation and form Cu2 plus 2 electron at anode. This Cu2 plus will reach us the solution. Due to the negative charge in anode, they will migrate towards cathode. At cathode, what will happen? These Cu2 plus ions will accept 2 electron and get reduced to copper. And they will get deposited on this pure strip. So after this process will continue, after some time the size of this thin copper strip will increases and the size of the big copper strip will decreases, and here we will get pure copper as anode. And the impurities will remain in the solution and they are called anode mud. So this method is called electrolytic refining. For refining electrolytically, a thick block of impure metal is taken as anode and a thin strip of pure metal is taken as cathode, and they are connected to electricity, a power source, and it is dipped in a solution of electrolyte. We are usually using the same metal solution, otherwise the same metal may be get reduced at the strip. So to avoid that, we will always use the same electrolyte solution. Here we are using copper sulfate solution. On applying electricity, the copper from anode undergo oxidation, forms Cu2 plus 2 electron. They will go to the solution. From the solution, the Cu2 plus move towards cathode and undergo reduction and form metallic copper. So after some time we will get a thick block of pure copper from cathode, and the anode mud, all the impurities will remain below the anode and they are called the anode mud. This method is called electrolytic refining. The same method we can purify silver. We can purify all good conductors. Then fourth one, that is called zone refining. Zone refining is usually used for purifying or making ultra pure metals. So the metals which are used in electronic devices like silicon chips, etc. must have 100% purity. So that type of metals can be purified by this method, zone refining. For example, all metalloids, that is silicon, germanium, boron, tellurium, etc. can be refined by zone refining. In zone refining, it is based on the solubility or crystallizing properties of liquid metal and impurity. That is, on melting, both metal and impurities will become liquid. Then on cooling, metal will crystallize first, then impurities. Then only we can use sound refining. So a rod of metal is taken, impure metal. For example, we can consider impure germanium. And we are using a circular heater. Using a circular heater, we are heating the metal from one direction and then moving to another direction. When the circular heater is here, the metal and impurities at this position will become liquid. They will become melt. And the circular heat is moving towards another direction. Then at that moment, the metal, there is a cooling effect happens because heater is moving to the other direction. Then metal will get solidifies or crystallizes, but the impurities, which less crystallizing property, will move with the circular heater. So we are continuing this process. We are moving circular heater from one direction to this direction. This process we are repeating for so many times. After repeated heating using circular heater, when we cut, on the one side we will get the pure metal and the other side we will get the impurities. So this method is based on the crystallizing properties of melted compounds. So on melting both will become liquid, but on cooling metal will crystallizes faster than impurity, then only we can use sound refining. So a circular heat is moving over a rod of impure metal. On moving the circular heater from one side to another side, impurities will also move along with the circular heater, leaving behind the metal. It will crystallizes on that side. So we'll get, on cutting in two halves, we'll get a pure metal on one side and a impure metal on the other side. This is called sound refining. This method is usually used for semiconductor purifying semiconductor metals, that is silicon, germanium, arsenic, etc. Then the fourth method. Fourth method is vapor phase refining. Vapor phase refining means the metal, impure metal, is treated with a particular reagent. By combining with that reagent, it will form a vapor or a volatile compound. Then after that, that volatile compound is decomposed and produce metals. So this method can be used for only those metals. They can form a volatile compound with a particular reagent. There are two requirements. First, they will form a volatile compound with a reagent. Second condition, this volatile compound must be easily decomposable. Then only we will get the metal. So there are two methods. First one is Mons process. Mons process is used for the purification of impure nickel. In this method, nickel is treated with carbon monoxide at a temperature of 330 to 350 Kelvin. This is impure nickel. It contains lot of other impurities, but only nickel will react with the carbon monoxide and form nickel tetracarbonate. Nickel tetracarbonate, it is a coordination compound. Then this nickel tetracarbonate, on heating to 450 to 470 Kelvin, it will decompose and produce nickel and carbon monoxide. It is a gas, it will expel off, and here we will get a pure nickel. So metal must form a volatile compound with a particular reagent. Then that volatile compound is decomposed by using heat, we will get pure metal. So impure metal of nickel is treated with carbon monoxide at a temperature of 330 to 350 Kelvin. It will form nickel tetracarbonyl or tetracarbonyl nickel. This nickel tetracarbonyl is collected, it is volatile, so we can collect it by passing through a tube or something like that. Then this nickel tetracarbonyl is again heated to still a high temperature of 450 to 470 Kelvin. We will get pure nickel. Because the byproduct is carbon monoxide, so no need to separate from the byproduct, it will easily expel off. That is called the Mons process. One more process is there in vapor phase refining, that is Van Arkel method. Van Arkel method. It is also the same principle. It will form a volatile compound, then easily decomposable. Here we can use titanium or zirconium. Titanium or zirconium can be purified by using this method. Zirconium or titanium is treated with iodine. They will form zircon tetraiodide. Zircon tetraiodide. This zircon tetraiodide, this only impurities will form this compound. Sorry, only pure metal will form this compound. This on heating, we will get zircon and iodine. So impure zircon on heating, the only zircon metal combined with iodine will form zircon tetraiodide, a volatile compound. This volatile compound is separated and on heating it will decompose and produce pure zircon, and the byproduct is iodine. At high temperature it will vaporize off. So this method is called Van Arkel method. So there are two methods we are discussed in vapor phase refining. That is Mons process is used for the purification of nickel, and second one Van Arkel method, it is used for the purification of zirconium, or the same method we can use for titanium also. The condition is the metal must form a volatile compound with a particular reagent. Second, it must that obtained volatile compound must be easily decomposable. Then the last method. In the case of D block and F block elements, we know that their chemical properties are almost similar because of their almost similar size. So we cannot use all these methods like liquefaction, distillation. All these methods are difficult for the separation of or purification of transition metals or inner transition, mainly inner transition F block elements. So in that case, we are using a very advanced technology that is called chromatography. There are so many chromatographic techniques are there. I will discuss only one here. It is based on the principle that components in a mixer have different adsorption rate towards a particular adsorbent. So we are taking impure mixer of metal. First we have to make it in gaseous state or in liquid state by dissolving in a particular solvent or by vaporizing it. So the liquid impure mixture of impure metal and impurities is allowed to pass through a adsorbent. This adsorbent is filled in a tube-like device. So that is called column chromatography. It is filled with adsorbent. Then we are putting the solution of impure metal mixture through the top of the chromatographic column. Then it contains metal, maybe some other metals, then non-metal, etc. There will be so many mixers are there. We don't know what are the impurities present. Then all these we can X, Y, Z. There are three components are there. Let it be three components: X, Y, Z. All these have different adsorption rate to the adsorbent filled in this column. So if X has more adsorption affinity towards this particular component used in this column, it will get stick first. X has more adsorbing tendency, or it has more affinity towards the reagent filled in the adsorbing. X will adsorb first. Then after some time the other one, let it be Y. Y will be adsorbed here, and Z, which has least affinity towards this reagent, it will adsorb here. So they are separated into three or more. That depends on the number of components present here. Then after that we are using an eluent. Eluent is a solvent which is used for removing these adsorbed components from the adsorbent column. Eluent is a solvent which is used for removing this adsorbed component from this column. So we are using that eluent. We have to select the eluent according to the nature of X, Y and Z. Using eluent, Z will easily wash off. First Z will wash off, Z will connected in a container. Then after some time Y will come, Y will connected in another container. Then after that, sometimes the same, we have to use more than one eluent. Using the same solvent, we cannot extract all the metals or non-metals. That depends on the nature. So by using different tests, we have to find the particular element that can be dissolved, each metals or non-metals present in that compound. So some cases using the same element we can separate. Some cases we have to use more than one element. So this type of chromatography is called column chromatography. Then it is based on the adsorption technique, so it is also called the adsorption chromatography. So this chromatographic technique is usually used for the metals which cannot be separated by the other methods we are already discussed. So see, these are the methods we can use for the purification of metal. First one is distillation. Second is liquation, then electrolytic refining, then sand refining, then vapor phase refining. There are two methods we are discussed, that is Mons process and Van Arkel method, and the last and the not least, it is called chromatographic technique. There are so many techniques in chromatography. We are discussing only one, that is column chromatography in the adsorption chromatography. It is coming under adsorption chromatography. Here we are using adsorbent filled in a column. That is why it is called a column chromatography. It is based on the principle that the different components in a mixer have different adsorption rate towards a particular adsorbent. Based on that principle, we are separating metals all over here. So we have completed the topic metallurgy. Thank you.